What's up everybody, today we are going to talk about gradient descent algorithm, especially for a simple neural network example we are going to look at, and by using that example we are going to kind of explore the idea of gradient descent. Okay, but quick warning, this is not related to this is not a backpropagation tutorial video. Backpropagation will not be explained in this video, but hopefully this will be a playlist, and in the future, in the coming days, I am planning on making some videos about backpropagation, which is a really important subject. If you have that tool on your belt, that would be very useful for you. Okay, so gradient descent, simply this we are going to look at an example. Okay, and here we have a function x1 and x2. We have two inputs, okay, and on one scalar output. All right, f of x1 x2, this is a function, right? So maybe this will be some ball like shape, like function, okay, and we will have a, okay, wait a sec, so two inputs and one output, okay, and I'm kind of assuming that you know what neural network is, but you don't need to know. Just, you know, follow. We can explore this in this video. All right, and we have this parameters for this specific problem, and we will employ two hidden layered neural network, and each one of those hidden layers will have 3 neurons, okay, and this is basically the general idea of that neural network that we're going to use. And here, 2 inputs and 1 output. Again, notice this is estimate of the output. All right, and we will some parameters, okay, but I don't want you to get, if you don't know what neural network is, first of all, don't get scared by that. This is just a gradient descent video, okay, this is not neural network video, first. And second, if you have any knowledge about like parameter optimization, okay, and again, that term shouldn't scare you. If you don't have any experience with that, it doesn't matter at all. And all right, and basically if you're like an engineering student, that should be enough. I feel like even the first grade should be enough. Okay, so you have some inputs and outputs, okay, and you will have some parameters, okay, and we have some observations, okay, we have some observations like in our every other case, every other parameter tuning or parameter estimation type of problems we dealt with in the back in the day, right? We have some data, okay, and by using that data, by taking advantage of that data, we will just estimate theta, and you can probably use gradient descent for that, and we will explore what it is and how to implement that for that specific problem. Okay, so these are the parameters that we should keep in mind for this problem, and the notation kind of gets complicated, and there are some differences among the different sources that I checked on the internet. And but basically I'm also looking at the Matlab's own notation, and this is your input number, input dimension, this is your output dimension, and you have also hidden layer list, okay. So by using this like 3 terms, you can directly, let me show you, plot, or I guess not plot, draw this structure, and you have again two inputs, okay, and you have one input, and these are your hidden layers. Again, notice in each hidden layer we have three. Of course, I've chosen this, number of neurons totally arbitrarily. Okay, it doesn't signify anything, but your hidden layer dimension is kind of two. Okay, you have two hidden layers, and then one comes from final layer, like output layer, and total you will have three layers. Okay, all right. So if you can also, you can draw those connections. Okay, but we are not going to be dealing with the artistic part of that. And okay, so this is the final output layer. Okay, let's check this first layer. Okay, and if let me zoom in. Okay, if you look at this, we have three neurons, and in the previous layer we have, maybe I shouldn't say layer, okay, but this layer takes two signals basically, okay, and output of it is equal to its neuron size, right? So that's why I written here two inputs, okay. Wait a sec. Here 1 2, we have two inputs, entering to that layer 1, okay, and three outputs, 1 2 3. Okay, that's great. Get rid of that, and by using those three parameters you can directly say this layer, and in each layer we have W and B, okay, and I'm going to explain what they are. Okay, I'm going to explain what they are. And for this layer, W matrix can be, or the size of it can be determined as, okay, here outputs, here this is 3 and this 3, okay, and outputs by input dimension, okay, here this is output and this is input dimension, okay, and like the number of rows for W and B matrices also should be equal to each other. And alright, okay, so let's check the second layer, layer number 2. If you look at this, there are three inputs and here three outputs for that specific layer. Okay, we have three inputs, three outputs, okay, and by using that three outputs, okay, let me get another color, okay, and three inputs, okay, and this is 3 by 1. This is always 1, by the way, okay, for B matrix. All right, and this is the final layer, layer number 3, okay, and in the previous layer we have three neurons, right? And let's see, yeah, we have three neurons, so the input dimension to this layer, layer number 3, is 3, okay, and the output of it, since we have scalar output, okay, is again equal to the, is 1, and by the way let me correct that. And we have 3 inputs and 1 output here. This is the output of the whole structure. Okay, and this is a scalar, by the way. Okay, so again 3 inputs, we can see that 1 2 3, right, and 1 output. Okay, so let's write down the dimensions of our weight and bias. This is called weight and this is called bias. Okay, matrices, right, 1 outputs, okay, 1, and this is 1. Okay, and let me get another color. Okay, this is 3 and this is 3, and this is always 1. Okay, so all right, whenever you have, let me get back to that. Okay, whenever you have number of inputs and number of outputs, the dimension of that are available to you, and you also design or chosen some type of hidden layer structure, 3 3, maybe 3 5, for example. You want 3 neurons here and 5 neurons in that layer, maybe. Okay, you can do that as well. And whenever you have that numbers, you can construct that diagram, and then you can determine the dimensions of the weight matrices, weight and bias matrices for each layer. Okay, you have. And okay, so let's try to look at the number of parameters that we need to tune. Okay, and here this is 3 by 2, 3 times 2 6, and 3 times 1 3. Okay, we have 9 parameters in that layer. Okay, and here 3 by 3 9, 3 by 1 3, and we have 12 parameters, and we have here 3 plus 1, we have 4 parameters. So all in all, what we need to tune is 25 parameters. We basically, the problem is this: for a given, let me 1 2, and this is the observation number 1. Okay, this is some number, this is some number. Okay, and this is observation number n, for example. Okay, for a given, and by the way, we have also 1 output corresponding to that. For a given n observations, try to tune those theta. We will later call them theta, right? We will have theta vector with 25 rows and 1 column. Okay, 25 dimension of vector. Okay, tune those 25 parameters. Okay, this is the problem. All right, so here, if you look at that part, we will have our function, okay, which depends on theta parameters that we will, continue, that we will try to change in each iteration. Okay, we will talk about what kind of iterations we are talking about. Okay, and what we have is the estimate of that function. All right, and by the way, you can call this model, right? This is your model in a way, and This is y estimate. This is y correct, y true, and you can subtract them and get the error, right? And square the error, and you can get the quote unquote cost. Okay, and cost of what? Cost of those terms, theta terms. Okay, because if, or later maybe I should rephrase that, cost of using not accurate parameters, because if your theta terms, if you really tune them right perfectly, your cost would be 0. Okay, and so you will tune, and again let me remind you, you have 25 parameters to tune, right? You will tune those 25 parameters and will check the cost, and you will tune those 25 parameters. You will tune like a knob, okay, and you will tune that term such that, and you will go into the direction where your cost is decreasing. Okay, here this is the gradient descent algorithm, and we are familiar with this because we in the previous videos, or I remember that we were talking about that back in the day. And here this is your current theta, right? And this is your alpha. You can call it like learning rate or something like 0.1 or 0.01, 0.001 type of number, right? And this J indicates cost, right? And you will basically take the derivative of J with respect to theta, okay? And what you have is a function of theta, and then you will substitute the current value of theta, and this will be a vector. Okay, so let's try to think about the dimensions. This is 25 dimensional vector, this is a scalar number, and this will be a 25 dimensional vector, column vector. Okay, so in this problem, in this example, we will look at the Matlab Codes Matlab Codes and some related information as well, and we will basically have 3 subroutines, 3 functions. Okay, so I call it like Q neural network or something, QNN, but this is our model. Okay, and here look at the structure. It has theta, it has parameters, its own, right, parameters, and it will take some input and then will output some estimate. Okay, so this is the structure. All right, and first we will code this, okay, and then we will look at the cost function, and here basically this structure, right? And what you need to have a cost, you need, first of all, let's look at the signals that is coming to that structure, right? Like x1, x2, or x, right? And then theta, the parameters, all right? And then correct output, or we can call it target, right? And so 1, 2, 3. Basically, we need 3 things. All right. Again, x input, okay, and parameters, theta, and target, okay, and it will give us the cost, okay. And as you can imagine, it's not that hard, right? We will talk about that in a moment. And maybe the most complicated part, you can say it like that, is gradient of theta. So And let me tell you, if you can like calculate cost, okay, that means you can, and if you're okay with like spending your time, and you can basically create gradient data. What does it mean? It means this term, the derivative of cost with respect to theta evaluated at current value of theta. Okay, and people call it theta, like gradient of theta. Okay, and okay, we will talk about this function, and this will be the main part of it. Okay, so here let's look at our model. Okay, and if you recall, we have three layers, right? And here we have our x1 and x2, like two-dimensional input vector, and this is layer 1, okay, layer 2, and this is layer 3, and this is final, or this is output layer, so we don't have any activation function in that layer. Okay, and let's look at the layer number 1. Okay, here I also named the like signals as z1 and a1, right? So this point basically w1 times x, okay, and we have b1 added to that, and we have z1, okay, right here, and we have sigmoid function, right? Sigmoid function is this, okay, and fun fact, like derivative of sigmoid is, okay, not that we're going to use that, by the way. This is not a back propagation video, right? This is the video about how would you like train a neural network with least efficient method. Yeah, this is okay. If you're into the extremes, this is an extreme video, because the training algorithm are not using gradient descent basic, or sorry, not using backpropagation algorithm. Basically, this, I guess, forces you to have that type of finite difference type of gradient descent algorithm, and you will see it is very inefficient. Okay, so the training takes a lot of time. Okay, why would we do that? We would do that, or we are looking at this problem. First of all, I think, I mean, this is my opinion, of course, and this is a good way to look at the structure of the neural network, first of all. Okay, and this is one, and this number two is gradient descent is an important algorithm to tune parameters or estimate parameters, and that's why you might like to check that video. Okay, and three, maybe you have a lot of time in your hands, right? Maybe, all right, and okay. However, let me justify my video as well. Okay, there might be some cases where, for example, backpropagation algorithm requires some type of structure in the system, right? What do I mean by that? For example, for example, okay, wait a sec. This is x1, this is x2, okay, x1, x2, okay, and you have three layers, sorry, three neurons in first layer, right? And corresponding to that, basically in that layer, you have, let's call it WL1, okay, so, and this is your input, and B. What is that? This is three-dimensional vector. Okay, all right, that's what's interesting about that. And then you will have sigmoid function. Yeah, sigmoid function as an activation for that layer. Okay, all right. So, and in the rest you have that type of structure. There's some structure to that diagram. You can see that, right? Okay, so maybe what you need to have for some reason, for some reason, is really complicated. Okay, and maybe let me get another color. Okay, maybe you have not sigmoid, but let me call it f1, f2, and f3. Really strange functions as an activation. Okay, for some reason you like to use leaky value and you like to use like value, right? And here in that activation, in the activation for that neuron, you want to use sigmoid, right? So as soon as you do that, your type of in a way your structure disappears. Of course, again there are like better algorithms to deal with those cases, but what I'm trying to say is that if you really like work hard, there might be cases where you would like to use that type of finite difference type gradient descent algorithms is what I'm saying. Okay, for example, maybe you have in the like layer 5, for example, you have 4 neurons, right? And this signal is forwarded or inputted to that, right? Feed through those layers for some reason. Okay, and then you have other layers. Okay, and what would you do if you have that type of cases? Of course, there are some ways to again deal with those cases, but yeah, first thing that comes to my mind is to use finite difference. Yeah, okay. Again, these are not like valid justifications in any way, right? I'm just trying to explain gradient descent by looking at this simple neural network problem. Okay, and okay, so where are we? All right, we are here. This is our first layer. Okay, here this is Z1. Here you can see Z1, and this is A1, right? You just use sigmoid function as an activation and tangent hyperbolic of Z1 equals A1. Okay, and you feed the output of that layer 1 to layer 2, okay, as an input to that layer 2, and here this is the layer 2 like equations, and this is the input to that layer, and this term is also input to that layer, and this term is input to that layer. This is layer 1, layer 2, and layer 3. Okay, the final layer is the output layer. Okay, so you can notice the similarity. Okay, and we use the same activation functions here, and this is final layer, and we have y estimate, and y minus y estimate basically gives us error, and by squaring it we have loss value. Okay, so this is the basic structure we have, and Question: how would you obtain this expression? Okay, how would you obtain it? So first of all, before answering to that, let me ask you, how would you determine the cost for a given theta? Well, you just use those theta values and then give the input to that model, okay, by you parameterized by theta value, and you obtain your y estimate, okay, and by using the targets and y estimate values you obtain the cost, okay, by using mean square error formula, okay. And we have 25 parameters to tune, right? And here theta 1, theta 2, and theta 25, okay. So this is your current theta, and you compute the cost corresponding to that value, okay, and you have some cost function, cost value, right? And in the, I guess, next stage, and what I'm explaining is like the critical part of this video, right? And you have like theta 1 plus epsilon, okay, and other values remain same, and then you calculate the cost, call it omega 1, okay, and this is going to be extremely boring, okay, and 5 cost, so you epsilon is like 0.11, 0.0001 type of small number, okay. So you just tweak that in a way, tweak that parameter and calculate the cost, right? And again you do that for theta 3, right? Theta 4, etc., and theta 25, okay. And then what you have is this, you have some current cost value, okay, minus J1 value, which is the cost we get by just tweaking the theta 1 value, okay, and divided by epsilon, okay. All right, and this is a number, this is just a number, okay. So you do the same for J2, okay, and again for J3, for J4, dot, and J25 over epsilon, okay. So what you have is a 25 dimensional vector, okay, and this 25 dimensional vector is basically your theta gradient, right? Or you can like write it like that, okay. Okay, all right, so let's, I guess, let's check the Matlab codes. All right, let me change the screen. Okay. Like Control plus. Okay, here. Let's look at the code, right? First of all, let's check the functions. There are 5 functions, okay? The code might look like long, but yeah, most of the first section is like totally just for educational purposes. Okay, you can delete them easily. All right, so this is the function where we use as a template, okay? And we will use that function to produce training values, right? Another right buzzword, and use this function to produce observations. All right, so let's look at that. What is the first function? This is function number 2. Okay, maybe I should mark it like that. Okay, let me get that function number 1, 2, 3, and 4. Okay. But what we need to look at is, like, we have 3 functions to look at. Okay, this is the first function that we need to analyze. Here, QNN, for some reason I named it like that, because I'm gonna give you some secret. I am planning on studying reinforcement learning, and Q learning is a type of learning algorithm, but you need to be able to learn that. You need to kind of know what neural networks or how to train neural networks, right? You need to know those type of things, and that's why I name it like that. And okay, so your neural network basically is parameterized by the values that we called theta, okay? And we calculated the dimension 25. It was 25, right? And we know why it is. And this is 2-dimensional input. Okay, so construct weight and bias matrices using theta parameter vector. Okay, so we have layer 1, okay, layer 2, and layer 3. All right, so first what you need to do is just allocate your parameters to these weight and bias matrices, okay? And I don't think this is complicated, right? But you need to be careful about the arguments. All right, so this is WL1, okay, and BL1, okay. All right, same thing for layer 2 and bias of that layer, okay. And again, be careful about the dimensions, right? This is the layer 3 weight and bias terms. I feel like you are able to see that. Okay, so now we have like weight and bias matrices for each layer. We can calculate, right, the estimates. Okay, so 1, 2, and 3, right? We have looked at those equations, right, on the tablet, and maybe I should, okay, get back to that. Okay, here you can see, right, this is literally what we typed in Matlab. Okay, let's change the screen. Okay, here x times weight, okay, and we add bias to that, and we have z term of that layer, and then by using that activation function we have the a value of that layer. All right, and this is layer 1, and since this is layer 1, the input of that layer is x, like input of the whole system. All right, here output of that layer is the input to the next layer, which is layer number 2. All right, and again here, this is the output A2. Okay, output of layer 2, and output of layer 2 is the input of layer 3. Okay, and we don't have any activation because this is a output layer. All right, so this is the model and this is the parameters. Okay, we have 25 parameters and we will tweak them and to find the gradient of theta, and by using that gradient vector we will update our theta to have better estimates of our parameters. Okay, and our prediction values later. Okay, so what was the second function? Yeah, this is the second function that we need to look at, and this is the cost function. So you have input and target is like the output. Okay, correct output. You have input and correct output target, and you have parameter. All right, 25 dimensional vector, and you basically, by using your model, you generate your y estimate, right? And this is the correct output and this is the estimated output, and by using those two terms you obtain error and you square that. Okay, and then since we will look at the batch input and batch output objects, all right, and so maybe you are thinking, but isn't it that scalar, right? Why are we like summing that? And because we will look at that in a moment, but we will give a bunch of inputs, right? Observations like n, capital N observations, and we will get capital N predictions from that model, and by using capital N target values we will compute the cost corresponding to that capital N number of observations, right? Or our data. Okay, it is called batch gradient descent, right? And stochastic, it is, yeah, stochastic gradient descent is the type of gradient descent that you do. You update your parameters after seeing each observation. Okay, you see observation, one observation, and then you update your data. But in batch gradient descent, you get like whole batch of the inputs and you produce by using same data, right? By using same data you produce all of the outputs, right? For example, you have 1000 inputs, right, and 1000 output values, and by using that the same theta value you produce 1000 estimated output, and then by using 1000 target values and 1000 prediction values you obtain mean square for that. Okay, this is how you calculate cost, and by that tweaking algorithm that we talk about, you obtain the gradient value, gradient of theta for that batch of data. Okay, and to take the mean, take the average, you can divide it by the number of observations that you have. Okay, again this is called MSE, mean squared error. Okay, so this is the gradient theta function where you generate the derivative of cost with respect to theta evaluated at the current value of or given value of theta. Okay, so for this object you need to have input, targets, and your current theta. Okay, and epsilon is like the term that we talk about. Okay, and this is theta dimension. All right, here we are just creating e vectors. You remember we use e for example, E4, right? E4 is a vector, is a column vector where all of the values are zeros, but except for the fourth entry, which is 1. All right. So this basically does that. Okay. Here, this is Matlab cell notation. Okay. Here, I mean, I guess it is not that complicated. Yeah, just cell notation, right? Okay. I don't want to dwell so much on that. So this is gradient value. We just allocate some memory for that, and then we will, construct that gradient vector, gradient value, right? Which is 25-dimensional vector. Okay. And this is cost. Okay. Current cost. Like we call it J0. Okay. In the tablet. Okay. And here we just, let me show you. We just add some epsilon term to that parameter vector, and then we calculate the cost, right? And by using that, like, incremented theta value, cost, and current cost, and those step size, right? We have the value of, for example, this is, we are looking at theta third entry, for example. Okay. And if we do that, if we compute this term, we have the third term of our gradient vector. Okay. Here we can get that term into that gradient theta vector. Okay. Which is something that we will use to update the theta values. Okay. All right. So now we are aware of those functions. Okay. We can look at the main code. Okay. Wait a sec. Here we can see the main code. Okay. This is 2 input, 1 output, and 2 layer, two hidden layer. Okay. But we have, let me, 2 hidden layer neural network, but we have 3 layers in total. Okay. And the final layer is the output layer. Okay. And this says test if QNN function is working for a single data. Okay. Here, this is theta. We just generate 25-dimensional vector random, and we generate a 2-dimensional just input, right? And we input that, and we get the estimate. Okay. And let me run that. Okay. It's working, right? We can see that. And here it says test if QNN function is working for a batch data, right? Again, generate random theta values, okay, parameters. And this is like 5 consecutive input signals we, feed forward to our neural network, to our model, and we will get, what we need to get is 5 outputs, okay, corresponding to the output values, sorry, input values. All right, here we have 5 input terms, okay, sorry, 5 output terms. All right, so it says test if cost function is working for a single data. Okay, here this is theta, this is input, and this is target. We generate like target values just randomly, just to see if cost function is working properly. Okay. All right. Yeah. Okay, it's working. And again, this is for batch data. Okay. And we just input 5 x values, and we need to have 5 y estimate values, right? And we also have 5 target values, and by using that 5 model output and 5 target value, we will compute the cost. Okay, here, but cost of course should be a scalar number. Okay, and here it says test if gradient theta is working for a single data. Okay, here this is single data 1, right? And input itself is 2-dimensional, but output is scalar. Here we have again 25 randomly generated parameters, and this is gradient theta function. Okay, yeah, this is important. This is, we have 25 numbers here. Okay, so by using, and since this is 25 dimensional vector, this is a direction. Okay, by using that direction, okay, or the negative of it, by going into that direction, our cost will decrease basically. Hence the name gradient descent. Okay, by using that gradient vector, we will descend and we will decrease the cost function we have. All right, so it says test if gradient theta function is working for a batch of data. Okay, here again 5 inputs. We will input 5 different input signals or input terms, okay, input vectors, and then we will get 5 estimate values, and we also have 5 target values, and by using that cost, okay, and our gradient theta function, we will generate again a gradient vector. Okay, let me clean that, right, and run that. Okay, again we see a vector. Okay, and we will move along to the opposite of that direction. Okay, this is a vector, this is a direction. Okay, we will update our theta values. Anyway, we will talk about that more. Okay, so let's construct the training set. Okay, here we have 10,000 values, right? And this is the function. Okay, let's look at the plot and see the function structure of that function. Here, if you can see, it has a Gaussian distribution type of, structure. Okay, all right, so by using our model, but again we haven't updated any, or we haven't tuned the parameters. Okay, so by using those input terms, let's obtain estimate and let's plot that. Okay, here this is the output. If you notice, it doesn't look like a Gaussian function. Okay, and so we will tune theta parameters, so the outputs or that model will look like a Gaussian. Okay, right, so this is the first training, I guess the most primitive. I mean, what we are using is, by not coding any backpropagation, is of course as primitive as is, right? But on top of that, we are not employing any type of adaptive learning rate alpha, right? So this is the first thing that you will do probably, right? And again, if what you have is a really small scale problem, you know what, this really works well, yeah. But of course we are talking about 25 dimensional problem, and this is not a small scale problem at this point, right? Okay, and all right, here 100 times we will update our theta by using our batch input and batch output. Okay, this is theta. So this expression is the expression of gradient descent basically. Okay, theta minus alpha, like running rate, times partial j over partial theta evaluated at the current theta. Okay, all right, I guess I said it right. All right, and then this is the cost function. This is the cost function corresponding to that theta. Okay, and in each like iteration, just print that value on the screen. Okay, all right, here we can see this. Here the cost value, right, you can see that the cost value is decreasing. Okay, and you can see it is painfully slow. All right, so this is the training, like second algorithm, where we are employing some type of adaptive. Wait a sec, this is not theta, sorry, this is alpha. Okay, this is alpha. We need to update theta, of course. Theta shouldn't be fixed. Okay, alpha is the here alpha running rate. Okay, and okay, first get the current cost and store that and copy that to that previous cost function value, and again store your current value, right? This is previous theta, and update your theta value by using gradient descent algorithm. Okay, and get the current cost, and if your current cost is better than your previous cost, I'm sorry, not previous, the best cost, okay, just store your current cost as, or update your best cost and store that current theta value, right, as the best theta value, okay, that you achieved. And we are also implementing some type of adaptive learning rate scheme here, where if your current cost is better than your previous cost, which kind, of course you can disagree with that, which kind of means that things are going well, so we can kind of increase our learning rate. Okay, all right, it's not like we converge, so we need to decrease alpha, right? However, if your current rate is worse than your previous iteration, just kind of reset your alpha value, right? Here alpha is the learning rate. Okay, and then print them on the screen. Okay, here. Okay, again, if you look at that, these are cost values, right? In each iteration, by updating theta values, right, 25-dimensional vector theta, our cost values are decreasing. Okay, so, and this is the third, and it is like 20 lines of codes to that. And here, I mean, we have some type of, again, there's typo alpha, I didn't mean theta. Okay, by using momentum. Okay, what do you mean momentum? By using, for example, theta values are changing, right? Okay, we have 25 theta values, but let's consider only first entry of that theta value, and that theta value is kind of, if you plot them, right, if you were to plot them, you will see some type of continuous change, right? So change or update your theta value, but also keep in mind the previous changes or the trajectory of that theta term. Okay, so momentum, it has some type of like idea built into that. So gradient descent with momentum is this basically. Okay, and so this like 10 lines of code, they're same. Okay, here we are first computing the current cost, okay, and then storing that to the previous cost, or we are copying that, and we have also theta change previous, right? In the previous iteration, theta change value, right? Here, this is theta change, and okay, we will look at that in a moment. Wait a sec. Let me check my screen. Wait a sec. Okay, I feel like I should get back to that tablets, and okay, all right. So this is gradient descent. Okay, alpha, the learning rate, times derivative of cost j with respect to theta, evaluated at theta I. Okay, theta I minus 1. Sorry. Okay. All right. Okay, this is vector. This is vector, and this is also vector. This is like vanilla gradient descent. Okay, and now we are looking at gradient descent with momentum. Okay, this is change delta, change current theta change, right? Sub I, okay, equals alpha times learning rate times derivative of cost with respect to theta evaluated at this theta value, okay, plus beta. We have now beta term. It can be a number ranging from 0.1 to 0.5 or something, okay, times delta, okay, theta I minus 1, okay, the change in the previous iteration, okay, and this is your update. This is your update minus the change theta change. Okay, this is, let me call it gradient descent with momentum. Okay, right. So I'm looking at my code, and for example, previous cost. No, wait a sec. Theta change. Right. So this is what I called theta change, right? And this is what I called theta change previous. Okay. All right. Right. If you keep that, two equations in mind, and let me go back to Matlab. You will realize that those like 5 or so lines, they are identical to the equations, like gradient descent and momentum equations we just written on the tablet. All right, so let's run that. Okay, basically, but before that, this is theta change meaning delta theta I. Okay, and this is delta theta I minus 1. Okay, and we are storing that theta. Okay, we are keeping that, theta in the previous iteration. This is theta I minus 1 basically. Okay, and this is theta change, meaning delta theta I. Okay, and this is the exact formula that we written on the tablet. Okay, and yeah, this is the second exact formula that we written on the tablet. All right, and then we are again computing the cost for the updated theta value. Okay, so let's run that. Okay, again you can see it is incredibly slow, right? So I should maybe pause that. So I run a lot of iterations, right? And training takes a lot of time because this is a very slow way of coding a parameter tuning, okay, for the model we had, right? Which is 3-layer neural network. All right, so let's plot the neural network predictions. Okay, and here, of course, here we can see there are costs associated with that terms, but you can see the like Gaussian type of structure, but of course there are some like error terms. Okay, some addition of like iterations, like training and updating iterations are required. Okay, but all in all, this was the video about gradient descent, and the model, we analyze it and we use it as an example to implement our gradient descent algorithm. Okay, and I feel like that was a good example to learn about gradient descent. Okay, and again, you can find this code. Not that I think you would like to look at the code, but you can download the code from the GitHub link down in the description. Okay, and thanks for watching.